1945, 2 nuclear weapons detonated over Japan, brought it close to the Second World War. 17 years later, a different kind of nuclear explosion would alter the trajectory of the Cold War, only this one took place in the vacuum of space. The detonation known as Starfish Prime stands as a defining event in the space race, one that fundamentally reshaped our understanding of nuclear conflict. Its story is essential for comprehending the origins of modern space policies and the profound reasons why international consensus forbids placing nuclear arms in orbit. The focus of our journey today is the Starfish Prime test, the critical lessons it provided, and the legacy that prevents us from sending such weapons into space. During the early 1960 seconds, the United States initiated a program of 5 high-altitude nuclear tests collectively named Operation Fishbowl. The objectives behind this operation were twofold, serving both military and scientific interests. From a military perspective, the goal was to assess the viability of nuclear weapons as a defense against ballistic missiles. Planners also needed to understand how a space-based detonation might disrupt electronics, communications, and military assets on the surface. For the scientific community, the tests offered a chance to observe how a nuclear explosion would interact with Earth's magnetosphere and to measure the resulting electromagnetic pulse. Starfish Prime was the inaugural test of this ambitious series. On July 9th, 1962, from a location approximately 1,500 kilometers west-southwest of Hawaii, a Thor rocket ascended toward the heavens. It carried a 4-megaton thermonuclear warhead, a device with 500 times the destructive power of the bomb used on Hiroshima. To document the event, 27 smaller rockets filled with scientific instruments were launched in concert to capture data on the blast and its after effects. As the Thor rocket reached its target altitude of 400 kilometers, a height comparable to the modern orbit of the International Space Station, the warhead detonated. What followed was a spectacle of profound and eerie beauty. Ionized particles from the explosion cascaded into Earth's atmosphere, colliding with molecules and igniting vast auroras across the Pacific Ocean that were visible as far south as New Zealand. Over Honolulu, the clouded night sky was brilliantly illuminated for a full 6 minutes, as if a second sun had appeared at 11 p.m. The effects were felt on the ground as radio stations experienced interference. A lone siren was activated, and streetlights throughout Hawaii were disabled. To appreciate the significance of Starfish Prime, one must consider its historical setting. The early 1960 seconds represented a period of extreme tension in the Cold War, as the United States and the Soviet Union were locked in an intense competition for global supremacy. Each superpower was driven to surpass the other in military capability, political sway, and technological achievement. The space race had become a central arena for this rivalry, and by 1961, the Soviets held an advantage. They had launched the first satellite into orbit in 1957, and 4 years after that, Yuri Gagarin became the first person to travel in space. This placed immense pressure on the United States, which feared the Soviets might develop and deploy space-based military systems before they could. With tensions already high from incidents like the Berlin Crisis, both nations began to see the militarization of space as a means to secure a decisive strategic edge. This perception fueled a race to create nuclear arms, missile defense platforms, and other technologies suitable for deployment beyond the atmosphere. Military strategists were deeply interested in how nuclear weapons might be used in space and what consequences their detonation could have for global military doctrine. A primary area of concern was the electromagnetic pulse, or EMP, that a high-altitude explosion would create. An electromagnetic pulse is an intense burst of electromagnetic radiation generated by a nuclear blast, particularly one occurring at high altitude or in space. This pulse can induce powerful electric and magnetic fields with the potential to disable electrical circuits. Such an event could disrupt communications on a massive scale and inflict extensive damage to critical infrastructure like power grids, satellites, and radio systems. While scientists in the early 1960 seconds were aware that nuclear detonations produced EMPs, the full extent and potential for destruction were not yet fully grasped. Operation Fishbowl was designed to examine these effects in detail, Conducted from Johnston Atoll, the operation consisted of 5 high-altitude tests in total. 3 months after Starfish Prime, the U.S. carried out the 4 remaining tests in a rapid sequence over just 2 weeks. The second test, named Checkmate, was launched on October 20th, 1962. Its 20-kiloton bomb, similar in yield to the one used on Hiroshima, was detonated at an altitude of only 147 kilometers. This was quickly followed by Bluegill Triple Prime on October 26th, Kingfish on November 1st, and the final test, Tightrope, on November 4th, 1962. The Bluegill Triple Prime and Tightrope tests were smaller explosions, detonating at 48 and 23 kilometers respectively. Bluegill Triple Prime was intended to study the effects of such a blast in the lower atmosphere, specifically the mesosphere, while Tightrope was an anti-missile test conducted within the stratosphere. Given that NASA defines the boundary of space as beginning at an altitude of 80 kilometers, it could be argued that these particular tests were not technically in space. The Kingfish test, which involved a 0.41 megaton device, detonated at 95 kilometers above sea level. However, none of these subsequent explosions approached the magnitude of Starfish Prime. The immediate impact of that first test was an awe-inspiring sight for those who witnessed it. Auroras stretched across thousands of miles, and a silent fireball bloomed over Hawaii. The experience itself was unlike anything witnessed on Earth. When a nuclear weapon detonates in space, there is no shockwave to feel and no sound to hear. It does not produce a mushroom cloud or the telltale double flash of an atmospheric blast. Instead, there is simply a brilliant, expanding sphere of plasma that shifts through colors much like a lava lamp. As the Earth's magnetic field guides charged particles down into the atmosphere, they generate the vivid auroral displays that earned these events the nickname rainbow bombs. But the lasting effects of such an explosion are anything but benign. Starfish Prime impacted the Earth's environment in 2 significant ways. In 1958, the American space probe Explorer 1 had made a landmark discovery. Our planet is surrounded by 2 concentric, donut-shaped regions of intense radiation. Today, we know them as the Van Allen belts, named after the scientist who discovered them. These belts are composed of charged particles, mostly protons and electrons, which are captured and held in place by Earth's magnetic field. They form a protective shield around our world, deflecting dangerous solar radiation and cosmic rays by trapping high-energy particles carried by the sun's solar wind. The Starfish Prime explosion injected such a vast quantity of charged particles into the Earth's magnetosphere that it fundamentally changed the composition and intensity of the natural Van Allen belts. More than that, it created entirely new, artificial radiation belts that were stronger and far more persistent than the originals. The lingering effects of the test persisted for up to a decade, shortening the operational lives of several satellite systems and interfering with telecommunications. These new radiation belts were responsible for the destruction of 2 early satellites, Ariel 1, which was Britain's first satellite, and Telstar 1, the world's inaugural television broadcasting satellite. The story of Starfish Prime's impact, however, did not end there. A key consequence was its electromagnetic pulse. While scientists knew the detonation would generate one, no one could have predicted its immense power. Nuclear blasts emit gamma rays in every direction, creating what is known as a Compton current. When these rays encounter the Earth's atmosphere, they ionize air molecules, liberating electrons with high energy. Because Starfish Prime was detonated at an altitude of 400 kilometers, its gamma rays collided with atoms in the thin upper atmosphere, producing a cascade of these free electrons. Earth's magnetic field then accelerated this cascade of particles, which in turn generated a rapid and intense oscillation of electromagnetic fields. At such high altitudes, where the atmosphere is significantly less dense, the pulse can travel much farther than it would from a detonation closer to the ground. The EMP from Starfish Prime spanned thousands of kilometers, causing damage to electrical systems far from the explosion site itself. Nearly 1,500 kilometers away in Hawaii, the pulse caused streetlights to go out, disrupted telephone lines, and affected radio communications. This was a stark demonstration of how vulnerable civilian infrastructure is to such an event. Starfish Prime forced the world to recognize the destructive power of an EMP. The test revealed the deep susceptibility of electrical grids, communications networks, and satellites to a nuclear EMP attack. It became clear that if this capability were added to a strategic arsenal, it would grant a military the power to disable an enemy's infrastructure without direct contact or bloodshed. The explosion also released an isotope called cadmium-109, which was subsequently used to track the fallout and assess the resulting contamination. While tests on the ground typically leave a distinct, localized fallout pattern, the consequences of testing in space were global. Traces of cadmium-109 were later discovered in the rainwater of New Zealand, a finding that a 1966 article in the journal Nature attributed to Starfish Prime. Reports like this fueled significant environmental concerns regarding the long-term effects of space-based detonations on the planet's atmosphere and ecosystems. It is intriguing to note that Starfish Prime was not even the largest bomb the United States had ever detonated at the edge of space. That distinction belongs to the Teak test, part of Operation Hardtack 30 in 1958. With a yield of 3.88 megatons, it was more than twice as powerful as Starfish Prime and was detonated at an altitude of 76.8 kilometers. The blast turned night into day and severed many trans-Pacific high-frequency communication circuits. A report from the Defense Nuclear Agency on the operation explained that the test had destroyed the ability of the upper atmosphere's normally ionized layers to reflect radio waves back to Earth. The Soviets were also actively engaged in high-altitude nuclear experiments, conducting 7 space bomb tests over Kazakhstan between 1961 and 1962 under a program known as Project K. Their objectives and the resulting effects were very similar to those of the U.S. test. These detonations occurred at altitudes ranging from 40 to 300 kilometers, though none of the bombs were as large as their American counterparts. Their yields varied from 1.2 to 300 kilotons, with the largest being about 5 times smaller than Starfish Prime. On October 22, 1962, one of these tests, designated Test 184, involved a 300 kiloton missile warhead detonated at an altitude of 290 kilometers. The resulting EMPs ignited a fire that destroyed the Karaganda power plant and fused over 1,000 kilometers of shallowly buried power lines between Tselinograd and Alma-Ata. These lessons carried serious Cold War implications, underscoring the necessity for international agreements to prohibit nuclear testing in space. The unforeseen consequences of Starfish Prime ultimately prompted both superpowers to rethink their strategies regarding space-based nuclear weapons. Just 1 year later, in 1963, the Limited Nuclear Test Ban Treaty was signed by the U.S., the U.K., and the USSR. This agreement forbade nuclear weapons tests in the atmosphere, in outer space, and underwater, aiming to reduce radioactive fallout and curb environmental contamination. This was followed by the Outer Space Treaty in 1967, which banned the stationing of nuclear weapons or any other weapons of mass destruction in outer space. It also prohibited nuclear explosions in space or on celestial bodies, establishing space as a domain for peaceful exploration rather than military conflict. Our modern world has a profound dependence on space-based infrastructure. Satellites are the backbone of global navigation, communications, the internet, GPS, and much more. A nuclear explosion in space today would unleash chaos on the world below. Global commerce and trade routes would crash to a standstill. Our electronics and power grids would be fried, crippling critical services. Hospital equipment would cease to function. Millions of tons of food would spoil without proper preservation, and financial markets would collapse. The effects of a nuclear EMP would be far more catastrophic today than they were in the 1960 seconds, simply because our vital global systems and daily lives are so much more reliant on electronics. We have seen that various international treaties are now in place to forbid further nuclear explosions in space. But could a catastrophic EMP event still happen in some form today? In 1859, the world's largest recorded geomagnetic storm, known as the Carrington event, caused some remarkable things to occur. The northern lights were seen as far south as Cuba and Honolulu, and they were so brilliant that people in the northern United States could read newspapers by the aurora's light alone. The storm induced powerful currents in telegraph equipment across the U.S., with some sparks strong enough to start fires. Should a coronal mass ejection of a similar magnitude be directed toward us, it could produce effects very much like those of Starfish Prime. Fortunately, the probability of such an event is quite slim. A more likely risk is geopolitical in nature. Earlier this year, Russia drew headlines when it vetoed a UN resolution against placing nuclear weapons in space. Several news outlets have since reported speculation that Russia intends to position a nuclear warhead in low Earth orbit. John Plum, an Assistant Defense Secretary for U.S. Space Policy, has stated that Russia is developing a concerning anti-satellite capability. He described this as a new satellite that Russia is developing, which carries a nuclear device. This capability, he warned, could present a threat to all satellites operated by countries and companies across the globe, as well as to the vital communications, scientific, meteorological, agricultural, commercial, and national security services on which we all depend. Such an action would stand in direct violation of the 1967 Outer Space Treaty, an agreement that, while still in effect, unfortunately includes no formal mechanisms for enforcement. The fundamental purpose of these international agreements is to prevent the cosmos from becoming a battleground for nuclear weapons. Their principles must be respected to guarantee our collective safety and well-being. As space grows ever more integral to modern existence, the lessons from our past take on a greater relevance. Starfish Prime provided a stark demonstration of the devastating reality of weaponizing space. The resulting electromagnetic pulses crippled infrastructure on the ground, and the waves of radiation it unleashed lingered within our atmosphere for years, ultimately destroying satellites and contaminating the orbital environment around our planet. This experiment marked a significant turning point. From its aftermath emerged one of the most crucial lessons of the nuclear and space age. It became clear that space could be weaponized in ways that would affect not just individual nations, but all of humanity. This profound realization is why international treaties now explicitly prohibit the use of nuclear weapons in space. These agreements represent promises made to future generations, pledges that space will be preserved as a realm for discovery and peace, rather than one of conflict and destruction. It is for this reason that responsible and peaceful space exploration is so vital, allowing us to continue unraveling the universe's mysteries and making discoveries that inspire and unite us, free from the persistent shadow of total annihilation. On the 4th of March 2022, a mysterious rocket booster concluded its journey by crashing into the surface of the Moon. This impact was closely observed by members of the scientific community who had been tracking the booster since 2015 as it silently orbited our world. Upon impact, it created an unusual double crater that seemed to defy both precedent and any straightforward explanation. For other observers, however, the more compelling question was its origin. No nation came forward to claim responsibility for its launch. The event immediately sparked speculation about secret government programs, or perhaps shadowy corporations launching pirate satellites for a quick profit. But as the details emerged, the true origins of this mystery rocket pointed toward an unexpected and deeply troubling issue. It speaks to a rapidly approaching era in which space, rather than being a place of peaceful exploration, might instead become rife with danger and conflict. While this is a future that can hopefully be avoided, the first step is to understand what is truly happening up there. To begin, determining the origins of the rocket booster, designated W0913A, is actually one of the simpler aspects of this mystery. The evidence suggests it was not the jettisoned component of a secret government program. While detailed knowledge of every nation's classified space programs is not publicly available, the reality is that clandestine space launches are surprisingly difficult to pull off, making this explanation improbable. This difficulty arises because, for the past 70 years since the invention of the intercontinental ballistic missile, nations have become deeply invested in knowing when other countries are launching rockets. Throughout the Cold War, the overriding fear was that America and Russia might launch nuclear missiles at one another. Consequently, it became a matter of national survival for each to monitor the other's activities. This was accomplished with radar systems, but also through extensive spy networks. When Russia launched Sputnik 1-inch 1957, American intelligence was already aware of the event, even if that information was not immediately shared with the American public. In the decades since, radar and satellite systems have become so advanced that they can detect launches within minutes. It is now virtually impossible to send a rocket into orbit without someone noticing. Rockets, after all, are quite difficult to conceal. Even if a launch could somehow go undetected by official means, the vastness of space is under constant watch. Amateur astronomers across the globe observe the skies as a hobby, and it would not take long before one of them spotted an unknown object. A more successful approach for a secret mission would likely involve disguising the spacecraft as something else entirely. By launching it to appear as an innocent satellite, or allowing it to detach from a rocket as if it were mere space junk, it could drift through space hidden in plain sight. If the mystery rocket were part of such a deception, that narrative might seem more plausible. However, its true origin was likely uncovered through careful mathematics. Independent astronomers, tracking the mystery rocket's path as far back as 2015, were able to plot its course and then calculate its trajectory in reverse. By doing so, they could determine which nations it had passed over at various points in its history. This analysis initially led them to believe it was a stage from a SpaceX rocket, but that theory was later supplanted by a much more probable explanation, that it belonged to the Chinese Chang'e 5 T1 mission. The mystery rocket's orbit crossed over China on the very same day as the Chang'e 5 T1 launch, and its trajectory was an exceptionally close match. There was also corroborating evidence. At the University of Arizona, students at the Space Domain Awareness Lab used a Raptor's telescope to perform a spectroscopic survey of the object. By analyzing the light reflecting from its surface, they could evaluate the type of paint used on it. A comparison with existing records showed that it was a closer match to China's rocket style than to that of SpaceX. These converging lines of evidence led astronomer Jonathan McDowell to state he was 90% certain the mystery rocket had belonged to China. Yet, China issued a denial. When questioned by journalists, Foreign Ministry spokesman Wang Wenbin reported that, according to China's monitoring, the upper stage of the Chang'e 5 mission rocket had already fallen through Earth's atmosphere in a safe manner and had burned up completely. He added that China's aerospace endeavors are always in keeping with international law. Some astronomers believe China may have been innocently mistaken. It is also possible that the statement was not truthful, but if the evidence points so strongly in one direction, the reason for the denial is worth considering. Perhaps the final line of the statement offers the most vital clue. China does not want to be perceived as being in breach of international law. And this is where the issue broadens, pointing not to a single country, but to a worldwide problem. Many people may not be aware that international space law exists, but it does, even if it is somewhat patchy in its current form. The governance of space is composed of a collection of treaties, signed and ratified by various nations over many decades. These include agreements like the Rescue Agreement, which outlines the responsibility of nations to assist astronauts in distress, and the foundational Outer Space Treaty of 1963. This landmark treaty codifies into international law the right of all countries to explore space, and it also holds states accountable for the space-related activities of their citizens. A core tenet of the treaty is that celestial bodies, such as the Moon, must be used exclusively for peaceful purposes. This is the very agreement that prohibits any nation from placing nuclear weapons into orbit, which is a primary reason why no orbiting platforms armed with such warheads are currently positioned above our planet. The treaty further establishes that states are liable for any damage they cause in space, and mandates that they must prevent the harmful contamination of other worlds. It is likely this final provision that China was attempting to avoid violating. While the impact of the unidentified rocket on the Moon probably caused minimal harm, the optics of misplacing a rocket stage that later collides with another celestial body are certainly unfavorable. The possibility of terrestrial bacteria surviving on the rocket introduces a risk of contamination. A far more serious scenario would have involved the rocket components striking an active satellite, or, in a future where lunar bases exist, colliding with one of those outposts. In such a case, China would have been in clear breach of international law. The question then arises as to why this incident might signal a future era of conflict. After all, while it is a disappointing development, it is hardly shocking that a nation might conceal information to gain an advantage or to save face. The issue runs deeper than just the growing problem of orbital debris, although that is indeed a mounting concern. The true cause for alarm is that the body of space law is so loosely defined that the origin of a spent rocket could remain a mystery for so long. The existing international legal framework is simply not robust enough to guarantee the peaceful exploration of space in the coming years. What we have is a set of noble principles riddled with loopholes and ambiguities. Consider, for example, the Outer Space Treaty itself. As one of the cornerstones for the peaceful use of space, it has been signed by 117 nations, including the United States, China, Russia, and virtually every other country with a space program. The treaty explicitly states that outer space cannot be subject to national appropriation through claims of sovereignty, whether by use, occupation, or any other method. Yet, this principle is already facing challenges. A fundamental tension exists between this prohibition and the ambitions of a growing number of nations to establish permanent bases and conduct mining operations on places like the Moon. Constructing a base on another planet or moon strongly implies an attempt to stake a claim to at least a portion of it, which closely resembles an act of sovereignty. Likewise, claiming resources seems to be a clear form of appropriation. The United States Artemis Accords, now signed by 23 countries, try to navigate this issue by having signatories legally declare that they are not appropriating the resources they extract. However, other nations view this as a semantic workaround. Some perceive the American interpretation as a modern parallel to the enclosure movement in 18th century Britain, where land was unilaterally claimed as private property. Depending on which legal interpretation ultimately prevails, any nation that tries to extract lunar resources could find itself in violation of international law. This legal uncertainty, however, does not appear to be slowing anyone down. Furthermore, the Outer Space Treaty stipulation that space is reserved for peaceful purposes contains a critical detail. While it bans nuclear weapons and other weapons of mass destruction from orbit, this restriction applies only to that specific category. This leaves considerable latitude for the development of weapons of moderate or lesser destructive power, and such concepts are actively being explored. In 2003, a full 4 decades after the treaty was signed, the US Air Force proposed a system of 20-foot-long tungsten rods, informally named rods from God, that could be deorbited from space. These projectiles would plummet at speeds approaching Mach 10, striking with the force of a small tactical nuclear weapon, but without the radioactive fallout. They would also be harder to detect than a missile launch, arrive in a fraction of the time, and be nearly impossible to defend against. Ultimately, the idea was shelved due to its exorbitant cost, not because it was seen as a violation of international law. As our civilization becomes ever more dependent on satellites for commerce, communications, banking, navigation, and countless other applications, the militarization of space is becoming more common. Satellites are increasingly seen as a critical vulnerability in a nation's security architecture. Consequently, various countries are developing anti-satellite, or ASAT, missiles and corresponding defenses, allowing them to threaten the interests of others while protecting their own. This is an extraordinarily complex issue with unforeseen dangers. A conflict in space does not follow intuitive terrestrial logic. When Russia tested an ASAT missile on one of its own defunct satellites, the impact created thousands of pieces of debris in orbit around Earth. Some of these fragments could remain in space for years, and if they collide with other debris or satellites, those objects could in turn shatter, creating a cascading chain reaction known as the Kessler syndrome. If such a conflict were to become widespread, it could effectively deny the use of space to all nations. Interestingly, Russia and China have advocated for a treaty known as PAROS, which would ban all weapons of any kind from space. This proposal, however, has been met with resistance from the United States, which favors an approach more aligned with the philosophy of U.S. President Theodore Roosevelt, to speak softly and carry a big stick. An argument can be made that some measure of defensive force in space might be necessary, which only adds to the complexity of the situation. To say that there is a deficit of trust between the major superpowers at this moment would be a significant understatement. Beyond these geopolitical tensions, in January 2018, a US company called Swarm was denied permission by the Federal Communications Commission to launch 4 of its satellites. In response, Swarm simply went to India and launched them without governmental approval. This action did have legal repercussions. The FCC later fined Swarm $900,000. Yet, it sets a troubling precedent. As access to space becomes more affordable for companies with substantial financial resources and few ethical restraints, it may one day become profitable to engage in illegal space ventures. To protect the work of legitimate scientific and exploratory missions in space, it seems likely that some form of policing, backed by a credible means of enforcement, will eventually become necessary. A challenging reality, as many analysts have observed, is that nations tend to advocate for rules that allow them maximum freedom of action while simultaneously limiting the activities and ambitions of others. And yet, the domain of space is in clear need of more robust global regulation. If the world's nations cannot come to a consensus on a framework for future exploration, there is a substantial risk that space could devolve into a lawless frontier, a kind of Wild West marked by conflict. In such a scenario, the more noble pursuits of scientific discovery would almost certainly be cast aside. This would be a profound waste, especially since a concerted effort could make international law strong enough to prevent such an outcome. The agreements reached so far do show some promise. A key document, known as the Moon Treaty, designates the lunar environment as the common heritage of mankind to be used exclusively for peaceful purposes. Its resources, the treaty stipulates, could only be exploited under the careful guidance of an international regulatory regime. The issue, however, is that very few nations have actually signed this treaty. Critically, none of the countries with significant independent launch capabilities, such as the United States, Russia, or China, are signatories, which renders the treaty largely symbolic. There has been no agreement on what the proposed regulatory body would look like, nor is there a clear definition of what the common heritage of mankind truly entails. For space to be a safe realm for the generations to come, this ambiguity must be resolved. Deeper discussions are needed on these critical topics to prevent illicit activities and to curb escalating arms races in orbit. The organizations that launch rockets must be held accountable for tracking them. Ultimately, the leading nations of the world need to find more common ground on these matters. We should not aspire to a future where mysterious rockets can crash into the moon without explanation. Instead, we should envision a future where space is valued for its alien beauty, a place where its dangers are understood as purely natural phenomena. It should be a future where the moons and planets can be explored peacefully and equitably, rather than becoming objects of conflict and potential destruction. Perhaps it is time for humanity to mature, not just in its technological prowess, but in its civic responsibility as well. For many, the Apollo missions represent a golden age of space exploration. It was a decade filled with one incredible achievement after another, earning NASA and its astronauts a deep sense of respect and admiration around the globe. But just 1 year after its celebrated mission, Apollo 15 began to generate headlines of a very different kind. A scandal emerged that would shake NASA to its foundations, with accusations of smuggling, profiteering, and a severe lapse in judgment that led the space agency before a congressional hearing. This incident transformed a mission of valiant scientific purpose into a clandestine operation, staining NASA's reputation at the very height of the space race. The entire controversy centered on just 850 grams of paper. Here, we will delve into the story of the Apollo 15 postal scandal, exploring what made it so deeply troubling, how the affair was uncovered, and what its lasting repercussions have been for spaceflight. On November 14th, 1969, a German man named Horst Eiermann left his home in Florida and boarded a bus heading to the Kennedy Space Center. His destination was the launch of Apollo 12. By a stroke of luck, another German man happened to be on that same bus. His name was Hermann Seeger, a stamp collector and dealer who, it turned out, was from the same region of Germany as Eiermann. They quickly discovered a shared passion for space travel and became good friends. At that time, stamp collecting was an immensely popular hobby. NASA had even begun producing specially designed envelopes, known as covers, for each Apollo mission. which were postmarked on the day of the launch. These covers became such an integral part of the launch day experience at the Kennedy Space Center that printing machines would run from as early as 1 in the morning just to meet the demand. They served as wonderful keepsakes for astronauts, their friends and families, and for NASA employees. Some astronauts took the tradition a step further, carrying postal covers with them into space inside the command module, later giving them as unique gifts to their loved ones. Eiermann worked as a NASA contractor, which gave him connections to many people at the Kennedy Space Center, including several astronauts. He had tried on more than one occasion to convince Apollo astronauts to carry stamps and covers aboard their missions in exchange for payment, but he had not yet found success. Then, one evening in May 1971, while at dinner with the Apollo 15 crew of David Scott, Alfred Worden, and James Irwin, Eiermann presented a compelling offer. He asked the astronauts to carry 100 special stamp covers to the moon for Seeger, and another 300 for themselves. Seeger's covers were intended to be sold later as exclusive collectibles. For their part in the arrangement, each astronaut would receive a generous payment of $7,000, a sum that would be equivalent to about $54,300 today. The crew was hesitant at first. NASA's standards of conduct explicitly prohibited astronauts from using their official positions for their own financial gain or for that of anyone else. Eiermann tried to reassure them, claiming that crew members on many previous Apollo missions had engaged in similar practices. He also reminded them that NASA had recently restructured its employee benefits, a change that meant astronauts were no longer provided with life insurance. Space is an unforgiving environment, regardless of the number of safety protocols in place, and the job of an astronaut is inherently dangerous. Eiermann capitalized on this vulnerability, persuading them that the money could be set aside as a fund to care for their families if the unthinkable were to happen during the mission. It was, and remains, quite common for astronauts to carry personal souvenirs on their flights. Of course, all such items require pre-approval from NASA to ensure they are safe for spaceflight and comply with strict weight limitations. Alan Shepard, for instance, had brought a few golf balls and a modified club head, famously playing golf on the moon. Buzz Aldrin carried a communion wafer and a small vial of wine aboard his mission. Several other astronauts had taken postal covers on their flights for friends and family back home. All of these items had been approved by NASA before launch. In this context, accepting Eiermann's proposal might not have seemed like a major transgression. However, a critical event had occurred just a few months earlier. The crew of Apollo 14 had carried a number of silver medallions with them on their spacecraft without NASA's knowledge. This was part of a deal made directly between the astronauts and a production company, the Franklin Mint. After the mission returned, the Franklin Mint melted down some of the flown silver, mixed it with other metals, and began mass-producing commemorative medallions. The company then heavily featured the story that these medallions had been to space in its marketing, in a clear attempt to profit from the mission's prestige. The crew of Apollo 14 ultimately avoided any serious trouble because they had not accepted payment for their part in the arrangement, which meant the scandal did not become the deep stain on NASA's reputation that it might have been. The context of the time is crucial. This was all unfolding against the backdrop of the Cold War. Public interest in the space race had reached its zenith, elevating astronauts to the level of celebrities. Consequently, anything that could reflect negatively on American success or compromise NASA's integrity was considered unacceptable. In the wake of these events, Deke Slayton, NASA's director of flight crew operations, had explicitly forbidden the Apollo 15 crew from carrying any items into space that could generate profit for themselves or others. The agency simply could not risk another round of damaging press after the Apollo 14 medallion incident. Knowing this, it may seem surprising that the Apollo 15 astronauts eventually agreed to a deal with a German associate, but they did so only with the strict understanding that no sales would occur until after their careers with NASA had concluded. It is important to note that, separate from this agreement, another party approached the crew with a very similar proposition, a retired film director and avid stamp collector named F. Herrick asked Al Worden to carry 144 postal covers into space for him. Herrick proposed that the covers would be stored for several years and sold only after all the astronauts had left the agency. Unlike the German dealer, however, He offered Worden no financial compensation for transporting them. Trusting the man, Worden agreed to the arrangement as a simple favor for an acquaintance. He could not have realized at that moment how this single decision would set in motion a chain of events that would profoundly alter the trajectory of his life. On the morning of the launch, the Kennedy Space Center post office opened its doors at 1 a.m. EDT, a standard practice for an Apollo mission. Hundreds of stamped covers were brought in to be processed through the cancellation machine before being delivered to the astronaut quarters. Members of the flight crew support team then sealed the 243 officially approved covers, which included the 144 from Herrick, inside fireproof bags made of Teflon-coated fiberglass. As team lead, James Smotherman conducted his final inspections of the astronauts' personal preference kits. He discovered the 400 undeclared covers from the German dealer, Hermann Walter Seeger. Holding the unauthorized items, he mistakenly assumed they were the approved covers destined for the flight and gave them no further thought. He would later admit that he simply goofed, and with that, the illicit Seeger covers were slipped into David Scott's spacesuit pocket, bound for the moon. From the perspective of space exploration, the Apollo 15 mission was an extraordinary success. It marked the first flight to utilize the lunar rover, which granted the crew unprecedented mobility on the surface for their geological research. They also remained on the moon for nearly 3 days, a longer duration than any previous crew, which was made possible by engineering upgrades to the lunar module that allowed for a heavier payload. During the return journey, Worden executed the first ever spacewalk in deep space. While on the surface, Scott and Irwin had retrieved the Genesis rock, a pristine sample of the moon's ancient crust. The crew even cancelled a NASA-certified postal cover on the lunar surface as a tribute to the U.S. Postal Service. Yet, less than a year later, these remarkable achievements would be overshadowed by a sense of profound betrayal. Almost immediately upon Apollo 15's return to Earth, Seeger and Herrick went back on their word and began selling the postal covers. Seeger retained one for himself and sold the other 99 for $1,500 apiece in just 2 months, a sum equivalent to nearly $12,000 each today. Herrick also began arranging sales through various dealers in New York and Europe, with his covers fetching prices between $790 and $1,250, which would be between $6,000 and almost $10,000 in contemporary currency. In late October of 1971, a prospective buyer for one of Herrick's covers reached out to NASA for authentication. This inquiry caught Deke Slayton, the director of flight crew operations, completely by surprise, which reflected poorly on the agency. He instructed Worden to ensure there was no further publicity surrounding these covers, emphasizing that they had only been approved on the condition of non-commercial use. In response, Worden wrote to Herrick, insisting that he halt all sales immediately. He would later reflect that he had believed Herrick would honor his promise, calling his decision to trust a stranger a significant error in judgment. By the following month, news of the supposed Apollo 15 covers being sold throughout Europe had become widespread. The crew, who were then in Germany as part of an official NASA European tour, determined it would be improper to accept the $7,000 that Seeger had promised them. By that point, however, the American media had caught wind of the story, and the damage was already done. Slayton was incensed. His crew had directly violated his orders, leading to a public controversy that tarnished NASA's credibility. He reportedly described the affair as a major scandal and formally reprimanded Irwin, Scott, and Worden for their poor judgment. He also had them removed from their roles as the backup crew for Apollo 17. Their wings were effectively clipped, and they would never fly in space again, the most severe punishment an astronaut could receive. But the controversy did not stop there. As the media churned out one headline after another, a genuine concern arose that the publicity would reduce an otherwise successful scientific mission to an unethical quest for profit by the crew, or worse, by NASA itself. On August 3rd, 1972, the Senate Committee on Aeronautical and Space Sciences convened a hearing to establish the facts once and for all. The committee needed to address several layers of concern, starting with the astronauts' own conduct. The crew admitted they had acted without sufficient forethought in failing to declare the postal covers, and they maintained that they were unaware of the Germans' intentions to use them for commercial gain. However, a detail emerged about an event that occurred during the flight that cast doubt on their true motives. At some point in the mission, the 400 unauthorized covers had been moved from the main command module into the lunar module, which subsequently landed on the surface of the moon. In their testimony, the astronauts acknowledged that this transfer violated protocol, but claimed they could not remember how or when it had happened. Postal covers were typically kept inside the command module, so taking these specific ones to the lunar surface would have made them a prized possession in any dealer's collection, dramatically increasing their market value. This raised the unsettling possibility that the astronauts were not merely innocent participants in a businessman's scheme, as they had portrayed themselves to be. For the Senate, the situation was deeply concerning, particularly how NASA could have permitted such an incident to occur so soon after the controversy surrounding Apollo 14. The dispute over the postal covers painted a picture of an agency that was incompetent, seemingly unaware of its personnel's activities, what they were carrying on missions, and a culture where personal profit could overshadow the public trust. Even Deke Slayton found himself in a difficult position. It came to light that, despite his initial fury, he had not informed his own superiors about the unauthorized covers upon discovering them. This omission cast a shadow on his integrity, prompting speculation that he might have been involved in the plan, though no evidence has ever emerged to support such a claim. In an intriguing development, pressure from senior NASA leadership led the Senate to employ a little-used procedural rule, closing the hearing to the public on the grounds that testimony could harm the reputations of those involved, a move that only deepened the sense of suspicion. The consequences stemming from the hearing would cast a long shadow over NASA and its astronaut corps. The agency directed all its astronauts, both active and former, to surrender any postal covers they had taken into space. This included the remaining covers from the Herrick deal, as well as the 300 uncommercialized covers from Apollo 15. This seizure resulted in the suspension of 15 astronauts who, in the words of NASA Flight Director Christopher Kraft Jr., had broken faith with the agency and disregarded a direct order from Slayton. Today, while astronauts are still permitted to carry approved personal mementos on their missions, federal regulations expressly forbid items like coins, stamps, and other postal materials whose nature makes them susceptible to exploitation. Just as the matter seemed to have been settled, an unexpected development occurred 5 years later. In 1978, NASA received a private memorandum from the Justice Department. The memo advised that while the agency likely had the legal right to retain the confiscated Herrick covers, the matter of the astronauts' 300 covers, which were meant as gifts, was different. Because these items had been taken from the crew without due process, it was possible that NASA had infringed upon their constitutional rights. It was on this legal foundation that Al Worden filed a lawsuit against NASA in 1983, ultimately winning the return of the crew's covers through an out-of-court settlement. By every scientific measure, Apollo 15 was a triumph, yet its legacy was undeniably tarnished by a scandal that raised serious questions about NASA's competence and marred the public image of the astronaut as an infallible American hero. While attempting to profit from such a mission seems inherently wrong, there were many who staunchly defended the astronauts. According to Shopman, a specialist in postal history, some felt the crew was being unfairly disciplined for activities that were not entirely new within the agency. The Seeger covers are now scattered across the globe, held mostly in private collections. Only 4 have ever been offered at public auction, the most recent of which sold for more than $55,000 in 2014, a figure that would approach $70,000 in today's money. Still, the fundamental questions persist. Were the astronauts merely naive participants in a shrewd business venture, or were they actively seeking personal enrichment? Was NASA truly unaware of what was happening, or were more people complicit? It seems unlikely we will ever have the definitive answers. This episode highlights how even an endeavor as noble as space exploration is not immune to human opportunism. The same human nature that gives us curiosity, ambition, and ingenuity also contains the capacity for guile and self-interest. In that sense, the story serves as a powerful reminder of the importance of honor, honesty, personal duty, and dignity in public service virtues that are truly without price. A different kind of story, one you may not have heard, involves the Harlon J. Smith Telescope and how it was shot 7 times. The field of astronomy can be a place of surprising events, with profound discoveries being made constantly, but typically, the only thing being broken is new ground, and the only shots being taken are of the distant cosmos. It is extraordinarily rare for a telescope itself to become the target of a violent attack, and yet, that is precisely what transpired in 1970. This moment could have been a catastrophe for what was, at the time, the 3rd largest telescope in the world, an instrument that had been completed just 2 years earlier. What exactly happened? What could possibly motivate someone to fire a 9mm pistol at the glass mirror of an observatory at point-blank range? And perhaps most remarkably, how did a glass mirror of such immense scale withstand not only 7 gunshots, but also several blows from a hammer? I'm Alex McCollin, and you're watching Astrum. Today, we explore the only known instance in history of an observatory being shot. The story begins in 1963, as the space race was gaining momentum. NASA was evaluating the best strategies for visiting the planets of our solar system, a key part of America's ambition to surpass the Soviet Union. This technical challenge required far more detailed information about those distant worlds. Consequently, NASA began planning for a new generation of telescopes capable of imaging the very heavens its astronauts would soon travel to. It was at this juncture that Harlan J. Smith entered the picture. Described by his colleagues as a softly spoken yet driven man, Smith possessed a profound passion for astronomy. He had recently been appointed director of the McDonald Observatory, which is operated by the University of Texas and situated in the mountains near Fort Davis. In his very first official capacity, he successfully convinced NASA to provide $5 million to construct a new telescope at the site. The project moved forward, with production commencing in 1964 and reaching completion in 1968. This was a monumental undertaking. The newly finished instrument, with its 2.7-meter mirror, was the 3rd largest of its kind in the world. It weighed an incredible 160 tons and had a light-gathering power 250,000 times greater than that of the unaided human eye. Generally, while a telescope's electronic systems can be upgraded as technology advances, the primary structure is built to last for about 100 years. This longevity is crucial, as astronomical observations can sometimes span decades. For instance, some known exoplanets require 20 years or more to complete a single orbit, and undiscovered worlds could take even longer. The new telescope was designed to be a versatile, multi-purpose tool, but its primary function would be spectroscopy. The mirror itself was crafted from fused silica glass. While making glass might sound straightforward, fused silica is a unique material produced through a highly specific and technically demanding process. Creating the fused silica took nearly a year and a half, built up piece by painstaking piece through a method of plasma torch hydrolysis that used silica gas at temperatures of 1,700 degrees Celsius. After its segments were fused together in a separate 1,400 degrees Celsius process, the immense shape then had to be cooled back down to take its final form, a delicate procedure that required another 2 full years. The entire manufacturing process was designed to produce a mirror with virtually no internal stress, making it an ideal instrument for the work that lay ahead. This context is what makes the events of less than 2 years later so startling when a man named Jack Hyde attempted to put the observatory's telescope mirror permanently out of service. Hyde was an instruments technician, a recent arrival who had started his position at the McDonald Observatory on January 1st, 1970. His exact motivations for what he did remain somewhat unclear. He was in his 30s and had previously been employed at the prestigious Smithsonian Observatory in Massachusetts before traveling to Texas for the new job. His wife and 3 children, however, had gone to live in Nebraska, separating him from his family. The McDonald Observatory is situated high in the Davis Mountains, a location chosen for its profound isolation and elevation, which offered minimal light pollution and a thinner veil of atmosphere to look through. With the nearest town, Fort Davis, located about 27 kilometers away, it was customary for all staff members to live on site. This deep seclusion, combined with the distance from his family, may have exerted a significant psychological pressure on Jack. In addition to this, the working hours were long. Observatories always aim to maximize their scientific output whenever astronomical conditions are just right, a reality that could mean technicians and operators might find themselves working extended shifts of 48 or even 72 hours. This pace isn't entirely unexpected in the field. Operations could be suspended at any moment due to bad weather, excessive atmospheric dust, or powerful 100-kilometer-per-hour winds. And while the staff were undoubtedly passionate about astronomy, the combination of grueling, high-pressure work and profound personal isolation might offer some insight into why Jack Hyde appeared at the observatory. Just 1 month into his new job, he arrived at the telescope building at midnight, carrying a hammer in one hand and a 9mm pistol in his pocket. There are accounts suggesting that Mr. Hyde had been drinking that evening and was reportedly struggling with his mental health. On the night of February 5th, the observatory was quiet, with most of the personnel already in bed. Staffing levels at McDonald were typically lean in those days, and at the time of the incident, only a single telescope operator and one supervisor were present inside the building. Mr. Hyde gained access to the facility without any difficulty. As an employee, his presence wasn't questioned, and security was minimal because an event like this had never happened before. Upon seeing the supervisor, he fired a shot directly at him. In a remarkable turn of events, the bullet passed through the man's clothing and struck the wall behind him, leaving him physically unharmed. The supervisor, understandably, fled to get help. Hyde then threatened the remaining telescope operator, forcing him to move the instrument into a maintenance position, which brought the large mirror into an easily accessible orientation. Hyde then climbed into the telescope structure, produced his hammer, and swung it at the mirror's surface, fully expecting it to shatter on impact. What's intriguing is that Hyde's own area of expertise may have contributed to his failure. As an instruments technician, his work focused on the image-capturing cameras and equipment at the base of the telescope, not the primary optic itself. He was therefore unfamiliar with the unique properties of the mirror's glass. Instead of breaking, the 4.5-ton mirror repelled the blow, causing the hammer to bounce back and strike him. He did, however, manage to create a small, pear-shaped dent in the glass, but that was the extent of the damage. In a state of frustration, Hyde then aimed his pistol at the mirror and fired all 7 of his remaining rounds into it. Each bullet embedded itself in the glass, but none managed to penetrate more than a few centimeters. The mirror's incredible resilience was an unintentional consequence of its manufacturing process. Due to a scarcity of the fused silicon material and other technological limitations of the era, the mirror had been constructed by fusing together layers of smaller glass pieces. This method, born of necessity, had ironically created a material with properties similar to laminated glass. This structure, combined with its substantial thickness of 31.8 centimeters, rendered it effectively bulletproof. By this point, other staff members had arrived on the scene and were able to restrain Hyde, holding him until the local sheriff could arrive. Unfortunately, when the sheriff finally inspected the mirror, he mistakenly concluded that it was completely destroyed because of the large hole in its center. He didn't realize this central aperture was an intentional part of the telescope's design, and that the actual damage was limited to the much smaller bullet holes. Consequently, newspapers began running headlines, claiming the telescope was destroyed. This prompted the observatory's director, Harlan J. Smith, to issue an official report to the astronomical community, reassuring them that the situation was not nearly as dire as it sounded. Ironically, Hyde's shots had, by sheer luck, mostly missed the most vital parts of the mirror. To an untrained eye, all sections of a telescope mirror appear to serve the same function. However, the portions near its center are largely unused for achieving high resolution, as they are shadowed by other hardware components and are perhaps used only for a small amount of light gathering. It is the area near the outer ring that collects the light critical for imaging. Fortunately, this meant that only 3 of Hyde's shots had actually hit a critical area of the mirror. Given that these small, centimeter-wide holes constituted a tiny fraction of the mirror's total surface area, Mr. Smith was able to report that the bullet holes would reduce the light collecting efficiency by only about 1% and introduce a very small amount of diffraction. The telescope had not only survived the attack, but it had emerged from the ordeal almost completely unscathed in terms of its performance. Mr. Hyde initially faced the possibility of criminal charges, with a potential jail sentence ranging from 2 to 20 years. But when Director Smith learned about the mental health problems Mr. Hyde had been facing, he decided not to press charges. Instead, he chose to help get Mr. Hyde admitted to a mental health institution where he could receive professional care. It was a compassionate act, an indication that the director harbored no genuine ill will toward Hyde, perhaps because, fortunately, no real harm had been done to either any person or the machine. After he was eventually released, Mr. Hyde did not return to work at the observatory. The University of Texas engineers responsible for the mirror's upkeep found that the repair was remarkably simple. Using a small drill, they carefully bored out the bullets and then smoothed the edges of the holes to prevent any future cracking from developing. After that, they simply reapplied the reflective surface back onto the mirror and considered the job done. In truth, nothing more was required. The Harlan J. Smith telescope still bears these bullet holes to this day, a quiet testament to the incident. Despite its troubled start, the telescope went on to have an illustrious career. Images it captured helped to inform the plans for the Voyager missions, and it has also made huge discoveries in the field of exoplanet research. In a time before the discovery of exoplanets in great abundance was even imagined, the Harlan J. Smith telescope was already scanning the cosmos for these distant worlds. Its work contributed to the profound understanding that such planets are remarkably common. Its findings helped confirm the idea that there is perhaps at least one orbiting every star in the sky. It is with considerable relief, then, that the scientific world reflects on the fact that an individual named Mr. Hyde failed to achieve his destructive goal on one particular night. The loss to astronomy would have been immense without this instrument. This telescope was eventually dedicated to Harlan J. Smith, the director responsible for its construction. Fortunately, it emerged from that incident over 50 years ago with only minor damage, leaving behind a few physical reminders for visitors to observe. When considering these scars, its terrestrial post is far safer than the environment of orbital observatories like the James Webb Space Telescope. These space-based instruments must constantly endure the risk of micrometeor impacts on their delicate mirrors. The intriguing question of how an observatory withstands an attack from a 9mm pistol finds its answer in remarkable resilience. This durability is a testament to superior engineering and the strategic use of approximately 4 tons of specialized, bullet-resistant glass. This deeper insight was made possible by Coyne Gibson, the current manager of observing support at the McDonald Observatory, who shared his time and photographs for this account. Among the pioneers of the space age, Ham, the chimpanzee, holds a unique place in history. He was the very first hominid to journey into space, a true pathfinder, charting a course that would define the future of human exploration. What, then, was his story? Did he return safely from a groundbreaking voyage that carried him farther from our planet than any living being before him? I am Alex McCone, and this is Astram. Together, we will explore the incredible story of Ham and examine the enduring legacy of his historic mission. The origins of Project Mercury are deeply rooted in the intense space race that unfolded between the USSR and the USA. Each nation was engaged in a determined effort to achieve primacy in space, an accomplishment seen as a powerful demonstration of military strength. It was out of this competitive environment that NASA itself was born. Before Project Mercury, during the early 1950 seconds, spaceflight initiatives were conducted by the United States military. These early missions often sent mice and monkeys on ballistic flights to study the physiological impacts of extreme G-forces and weightlessness. The technology of the era was comparatively rudimentary. Early rockets like the Aerob 3 were quite small by modern comparisons, standing just 8 meters tall and reaching an altitude of only 60 kilometers. The animal passengers aboard would endure forces of up to 4 Gs during launch and then experience a few minutes of weightlessness. Observations suggested they were disoriented, but ultimately came through the ordeal with no lasting ill effects. The selection of monkeys for these tests was a deliberate choice based on their close physiological similarities to human beings. It was believed their reactions would provide a reliable preview of how a human astronaut might fare. One of the final spaceflights by the US military occurred in 1959. This mission successfully sent 2 monkeys, Miss Abel and Miss Baker, to an altitude of 570 kilometers aboard a Jupiter rocket. Their journey was an intense one, subjecting them to a staggering 38 Gs of force and a peak velocity of 16,000 kilometers per hour. The mission was deemed a success, and the nose cone was recovered intact. Unfortunately, a tragedy followed when Miss Abel passed away several days later from complications after a surgical procedure. In contrast, Miss Baker enjoyed a long life after her return. She even went on to have offspring as part of ongoing studies and was honored for her contributions. As a lasting tribute to her service, visitors often leave bananas at her final resting place. Just months after that flight, the newly formed NASA officially assumed control of the nation's goal to put a human in space through its ambitious Project Mercury. The program would utilize new launch vehicles, including the Mercury Atlas and the Mercury Redstone. The sense of urgency in America was palpable, heightened by the Soviet Union's landmark achievement in 1957 with the launch of Sputnik 1. After several years of rigorous testing, NASA determined that by 1961, the time had come to launch a hominid into space. The chosen vehicle for this critical step was the Mercury Redstone rocket. At 25 meters in length, it was substantially larger than the Aerob 3, yet still modest compared to the colossal rockets of our time. Its size was, however, sufficient to accommodate a capsule large enough for a human astronaut. A key limitation of the Mercury Redstone was its design for suborbital flight, meaning it could reach space but lacked the power to achieve a stable orbit. Selecting the right candidate for this mission was of paramount importance, as the chimpanzee was expected to be more than a passive passenger. He would be required to actively carry out specific functions during the flight. The successful performance of these tasks would be a crucial proof of concept, demonstrating that an astronaut could maintain control even if communication with ground control was lost. Out of a group of 40 potential candidates, one was ultimately selected through a meticulous process that prioritized health and obedience. The chosen chimp also possessed a calm and cheerful disposition, a valuable trait for such an endeavor. To shield the program from potential public outcry in the event of a failure, he was known only by his designation, number 65. His training was straightforward but essential. He was taught to operate a lever within 5 seconds of a blue light flashing. A correct response earned him a banana pellet, while failure resulted in a light electric shock to his foot. Following months of preparation, Ham was deemed ready for his historic journey. He was first secured inside a small, personalized capsule that functioned as his own spacesuit. This container was engineered to maintain a stable environment, regulating pressure, oxygen, and temperature for his safety. It was also equipped with sensors that continuously monitored his vital signs, transmitting this data back to mission control. The enclosure's design allowed his arms to remain free to access the controls for his tasks, and a small window provided him with a view. As the launch window neared, scientists and engineers conducted their final verifications to confirm all systems were nominal. Ham was then carefully transferred into the main capsule of the Mercury Redstone rocket, the same pressurized compartment intended for a human astronaut. With the arrival of dawn, the rocket lifted off. Barely a minute after leaving the launch pad, however, onboard computers began sending alarming data to mission control. The rocket's trajectory angle was already off by 1 degree and was continuing to climb. The rocket's ascent was unexpectedly steep, causing it to gain speed far more quickly than anticipated. Inside the capsule, the force of this acceleration was projected to subject Ham to an intense 17 Gs. Barely 2.5 minutes into the flight, the rocket's liquid oxygen supply was exhausted, an event that triggered a mayday alert to recovery crews. The vehicle was now in an uncontrolled spin, having climbed to a much greater altitude and reached a higher velocity than the flight plan had called for. In response to this dangerous situation, an abort command was issued, and the capsule separated from the rocket prematurely at an altitude of 250 kilometers, well above the planned 185. A critical consequence of this early abort was that the retro rockets, designed to slow the capsule, never fired. Ham's craft was now plummeting back toward the planet. As if the situation were not dire enough, sensors indicated a rapid loss of pressure within the main capsule. This was later traced to a faulty air inlet snorkel valve, where a pin had been shaken loose by the launch vibrations. Through all of this, Ham himself remained oblivious to the unfolding crisis. His own self-contained life support capsule protected him from the depressurization of the larger craft, and he calmly continued to perform his trained task, manipulating a series of levers in response to light cues, with his performance only marginally slower than his baseline results on Earth. As the capsule re-entered the atmosphere, Ham experienced another period of intense G-forces, this time peaking at 14 Gs. The absence of the retro rockets meant the capsule greatly overshot its intended splashdown point by 100 kilometers. Its parachutes deployed successfully, and airbags at its base inflated to soften the impact and provide buoyancy. When it struck the ocean, a colored dye was released to make it more visible to recovery teams. An agonizing 12 minutes passed before the capsule transmitted its first recovery beacon signal. 27 minutes after splashdown, a search aircraft finally located the capsule bobbing in the Atlantic. The US Navy dispatched rescue helicopters from the closest vessel, but by the time they arrived, the craft had taken on significant amounts of water and was beginning to sink. The force of the landing had dislodged the heat shield, which in turn tore through the capsule's base. The flotation airbags were heavily damaged, and that same leaky snorkel valve was now allowing seawater to flood in. By the time it was finally hoisted from the ocean, the capsule contained an estimated 360 kilograms of water. After a 3-hour recovery operation, the craft and its vital occupant were airlifted to a nearby Navy ship, where NASA scientists anxiously waited. With so much having gone wrong, the central questions were whether he had survived, and, if so, what his physical state was. Navy personnel and scientists moved with urgency to open the capsule. Once the hatch was removed, they found Ham was perfectly fine. He had made it through the ordeal safe and sound, seemingly his usual cheerful self, as though nothing extraordinary had occurred. He had endured everything with almost no harm, his only injury being a small bruise on his nose. Ham's career as an astronaut ended shortly after his historic flight, and he went on to live for another 20 years in several zoos, passing away in 1983. His skeleton was preserved for study at the US National Museum of Health and Medicine, while his other remains were interred and honored at the International Space Hall of Fame in New Mexico. The success of this mission paved the way, just a few months later, for the United States to send Alan Shepard into space aboard another Mercury Redstone rocket, Freedom 7. Yet, in this particular contest, the US did not claim the ultimate prize. The Soviets achieved the first human orbit of the Earth with Yuri Gagarin aboard Vostok 1. The legacy of these early efforts, however, continues to resonate, with humans now living aboard the International Space Station and a new space race underway to return to the Moon. And that is the remarkable story of the chimpanzee who ventured into space before any human from his country. If one were prone to superstition, it might be wise to be cautious about the names given to space missions. When Russia announced its first lunar mission in 47 years, the project was initially designated Lunar Globe, which translates to lunar sphere. This name, however, troubled Lev Zeleny, the scientific director of the Russian Academy of Sciences Space Research Institute. The Russian word glob sounded uncomfortably close to another word, grob, which means coffin. Zeleny consequently changed the mission's name to Luna 25, a deliberate choice to evoke the legacy of the earlier Soviet lunar program, the last time a Russian craft had successfully touched down on the Moon. But perhaps the change came too late, as if some shadow of the original name remained. We now know that Lunar Coffin would have been a far more accurate title for the ill-fated Luna 25. I'm Alex McCone, and you're watching Astrum. Today, we will investigate the outcome of Russia's first attempted moon landing since 1976. For a nation that was once a leader in the race to the stars, what precisely went wrong? While we often focus on missions from NASA or ESA here at Astram, Russia's space program has a long and formidable history. When Russia was the core of the USSR, it was the Soviet Union's 1,957 launch of Sputnik 1, the world's first artificial satellite that ignited the space race. For a period, the Soviet space program seemed to advance from one triumph to the next. It was the Soviet Union that sent the first man into space, followed by the first woman, the first crew with multiple people, and the first dog. Their rockets were the first to break free of the Earth-Moon system, the first to make contact with the Moon, the first to orbit it, and the first to capture images of its far side. Soviet cosmonauts performed the first spacewalk and the USSR launched the world's first space station. In the eyes of the world, and to the great satisfaction of Soviet leadership, the USSR appeared to be winning the space race. Beneath this veneer of success, however, the reality was not nearly as seamless. The Soviet Union was also the site of the first death during a space mission, when cosmonaut Vladimir Komarov's re-entry capsule parachute failed to deploy. The only 3 individuals to have ever died in space itself were a Soviet crew returning from that very first space station. Soviet launches were beset by frequent failures. However, driven by a desire to project an image of superiority, especially in comparison to its American rival, the USSR adopted a policy of silence. It simply did not announce any of its failed lunar missions. Any rocket that exploded before leaving the atmosphere was retroactively described as never having been a moon mission in the first place. In truth, only about 34% of Soviet lunar missions were successful. This stands in contrast to America's 60% success rate on comparable missions. It was America that ultimately landed the first human on the moon in 1969. Following that monumental success, the intense rivalry that had defined the space race seemed to dissolve, with both superpowers redirecting their programs toward objectives beyond the moon. By the middle of the 1970 seconds, no Soviet cosmonaut had ever walked on the lunar surface. The USSR ultimately shelved its plans for a crewed landing, viewing the undertaking as prohibitively expensive. A more subtle, yet powerful factor was the question of prestige. There was little motivation to invest so much only to arrive in second place. Yet, with the dawn of a new millennium, and particularly after the 1991 dissolution of the Soviet Union, global interest in lunar exploration experienced a significant resurgence. Scientists began to see the moon in a new light, not as a finish line, but as a crucial waypoint for future human missions to Mars. Its potential resources, especially the newly confirmed presence of water ice, became a major focus for their value in creating rocket fuel, breathable air, and drinking water. This, combined with the moon's low gravity, started to capture the attention of private businesses for economic exploitation, while various nations contemplated the establishment of permanent bases as a profitable venture. And, of course, a vast amount of scientific work remained, drawing researchers eager to better understand the moon's formation and the natural cycles that shape its environment. Russia's historic rival, the United States, began to reinvigorate its own space initiatives. In 2005, America launched its Constellation program, officially stating its goal to return astronauts to the moon. This time, however, other countries were entering the field. India, which had not been a participant in the original lunar race, initiated its Chandrayaan program for lunar exploration back in 2000. A consensus was forming among governments worldwide that the advantages of this second push to the moon were so profound that nations failing to participate would risk being left behind. The sentiment was captured by Israel chairman Krishnaswamy Kastarangan, who suggested that the real question was not whether a nation could afford to go, but whether it could afford not to. Russia had no intention of being sidelined and was keen to embrace the Soviet legacy of space exploration. In fact, it had anticipated this new wave of interest. Russian scientists had already been contemplating a new lunar mission as early as the mid-1990 seconds, when Mikhail Mavrov and Eric Galimov presented proposals to Roscosmos, the country's newly reorganized space agency. Their Lunar Globe mission received approval and was originally conceived with multiple components, including a penetrator for seismic analysis, a lander, and an orbiter. The project, however, initially struggled to gain sufficient political backing. It suffered from budget reductions following the 1998 Russian financial crisis, during which the ruble's value plummeted by over 2/3 in just 3 weeks. The mission became mired in delays that repeatedly pushed it back and put it on hold. To make the plan more economically feasible, the mission was reimagined, and the penetrator and orbiter elements were eventually scrapped, leaving only the lander. Russia aspired to be a recognized force in space exploration, but was unwilling to commit a massive portion of its budget to the goal. For perspective, in 2005, Russia's investment in its space industry was only 20 billion rubles, equivalent to about $700 million, a stark contrast to the $15.6 billion allocated by the USA. One strategy to overcome this financial constraint was through international collaboration. Russia first attempted to partner with India on its Chandrayaan-2 mission in 2007, where the plan was for Luna 25 to serve as the lander accompanying India's orbiter. Ultimately, this lower level of spending proved detrimental, as Russian scientists could not get the lander's technology operational in time for the planned 2013 launch. India eventually decided to proceed without Russia, completing Chandrayaan-2 independently. This left Russia in the position of trying to land Luna 25 on the Moon by itself. Although India's Chandrayaan-2 lander ultimately crashed, the nation was determined to try again with Chandrayaan-3. This sequence of events transformed Russia and India from collaborators into direct competitors. Both nations had their sights set on the Moon's south pole, a region where Chandrayaan-2 and other missions had confirmed the existence of water ice through spectrometry. Luna 25 and Chandrayaan-3 were now in a new race, to become the first to successfully touch down at the lunar south pole and perhaps directly analyze that ice. Russia, however, soon faced a new and formidable obstacle with the 2022 invasion of Ukraine. Western nations responded with outrage, imposing sweeping sanctions against Russia. These measures were economically damaging, but a critical component was the ban on trading high-end computer chips and electronic components. While intended to hinder Russia's ability to develop high-precision ballistic missiles, the sanctions also dealt a blow to its lunar ambitions. European scientists started to terminate their partnerships with Roscosmos. In a deeply interconnected global economy where Russia had long sourced many of its advanced components, the nation would now have to proceed in isolation. India completed Chandrayaan-3 and launched it on the 14th of July 2023. The trajectory chosen for the mission was highly fuel-efficient but slow, requiring over a month to reach the lunar surface. India projected a landing date of August 23rd. This long journey created an opportunity for Russia. If it could move quickly, it could use its powerful Soyuz 2 1B rocket to take a shorter, more fuel-intensive path and arrive first. The Luna 25 mission had already been postponed from 2021 to 2022 and then again to 2023. In a stroke of bad fortune for Russia, its BIB navigation sensor failed quality control tests. This was a significant problem because the sensor depended on a computer chip that was normally sourced from the West, a chip Russia could no longer acquire due to the sanctions. In response, Russian scientists were forced to develop a new sensor, the BISL, entirely on their own. With the new component installed, Luna 25 was finally declared ready and launched on the 11th of August 2023. On board was a suite of 8 Russian scientific instruments, including laser mass spectrometers, infrared spectrometers, cameras for imaging the terrain, and a device designed to measure dust and micrometeors. The lander was engineered to operate on the lunar surface for a full Earth year, built to withstand the extreme cold of lunar nights and the harsh solar radiation of lunar days. It held the promise of conducting valuable science. The Soyuz rocket was powerful enough to deliver Luna 25 to the Moon's surface by August 21st, a critical 2 days before the scheduled arrival of India's lander. It appeared Russia was poised to win the race against its former partner. Luna 25 lifted off successfully from the Vostochny Cosmodrome on the 11th of August 2023 and entered lunar orbit on August 16th. It began its work by transmitting photographs of the Moon's surface, capturing images of the Zeeman crater. At that point, all systems were reported to be functioning as expected, and communications remained strong. With the spacecraft in position, Russian mission controllers initiated the final preparations for the landing sequence. The Moon's south pole is known for its challenging and unforgiving landscape, so the team was focused on ensuring a gentle touchdown to avoid any damage to the Luna 25 lander. But at this critical stage, something went awry. On the 19th of August, Luna 25 ceased all communication with ground control on Earth. Without remote guidance, the craft proceeded with an autonomous, pre-programmed maneuver designed to shift it from its circular lunar orbit into a descent trajectory toward the surface. It was during this operation that additional failures compounded the problem. The BISL navigation device, which had been developed in Russia after its predecessor failed quality control, fed erroneous data to the lander's onboard computer. This misinformation caused the thrusters to fire for 127 seconds, a significant deviation from the planned 84 seconds. The extended burn pushed Luna 25 into an increasingly steep and unrecoverable descent. By August 20th, the lander was plummeting toward the lunar surface at a velocity that was impossible to arrest. Scientists at Roscosmos could only monitor the situation helplessly as their spacecraft accelerated into the terrain below. While no cameras were present to capture the final moments, one can easily picture the inevitable outcome as gravity's pull transformed Luna 25 into a silent lunar tomb. Its mission, intended to mark a new era, had lasted not for a year, but for mere days. Sometime later, NASA's Lunar Reconnaissance Orbiter passed over the area, capturing an image that revealed the craft's final impact site. Luna 25 had struck the surface with immense force, carving out a new crater, approximately 10 meters in diameter. Russia had hoped this mission would demonstrate to the world its continuing prowess as a major power in space exploration. The reality, however, was that the Luna 25 project had been beset by immense pressures and difficulties from the start. Western sanctions had created indirect obstacles, and the replacement navigation system developed domestically was either not precise enough or not robust enough to withstand the harsh radiation of deep space. Beyond these technical issues, Russia's ambition to land on the moon before its rival, India, introduced its own set of complications. Learning that its arrival was scheduled just 2 days ahead of India's mission brings to mind a similar episode from the past. The Soviet Union's Luna 15 probe crashed into the moon on the very same day that Apollo 11 landed, and only a few hundred miles away. That earlier mission, Luna 15, had been given the same objective as the Apollo 11 astronauts, to collect lunar rock samples. Although it was an uncrewed probe, a success for Luna 15, especially in the event of an American failure, would have been a significant point of pride for the Soviet Union, effectively stealing the spotlight. The core motivation was political one-upmanship. The Soviet Union was not merely interested in reaching the moon. It was driven by the desire to be the first to achieve its goals. Inevitably, when the primary objective is to beat a competitor, less time is dedicated to ensuring every system functions with perfect reliability. This approach inherently increases the probability of failure. In the end, much like its predecessor Luna 15, Russia's Luna 25 achieved the very opposite of what the nation's leadership had intended. Instead of showcasing Russia's preeminence in space, it highlighted the profound disadvantages of isolationism and rivalry in an era that favors collaboration. Had Russia still been engaged with partners like the European Space Agency, sharing in technological progress, it might well be celebrating a successful landing today. In many ways, the outcome is a genuine tragedy. There is hope that this dynamic can one day shift. The future of humanity appears to be directed toward the stars. If we are to truly flourish in that domain, it will be because we have learned to work together as a global community. The unfortunate fate of the Luna 25 mission can and should serve as a valuable lesson, not just an embarrassing historical footnote, but that can only happen if the correct conclusions are drawn from it. Pride does not always serve us well. Rivalry can lead to an unnecessary isolation that clouds judgment and prevents careful planning. Though it may seem unlikely now, it would be a welcome change if our collective efforts to prove superiority could finally be laid to rest. Buried in a frozen crater on the lunar surface, the craft is a testament to these challenges. The endless frontier of space has always beckoned to humanity, with its vast, uncharted territories and its immense, untapped potential. From the moment the first human ventured into the great void, we have carried the dream of exploring ever farther, of pushing our boundaries beyond what was once thought possible. But an intriguing question is now emerging. What if the next frontier is not meant for humans to explore at all? What if the future of space exploration rests instead in the hands of intelligent machines? We will now delve into the compelling subject of whether artificial intelligence, or AI, could one day replace humans in the exploration of space. Since the dawn of space travel, human beings have been central to every mission. The rapid ascent of AI technology, however, is fundamentally changing that equation. Could artificial intelligence be the very key that unlocks the deepest mysteries of the universe, propelling our understanding further than we ever imagined? Or are humans still a vital component of space exploration, bringing with them unique skills and qualities that AI simply cannot yet replicate. I'm Alex McCone, and this is Astrum. Please join me as we investigate the cutting-edge developments in AI and consider its potential to completely revolutionize our exploration of the cosmos. Before we explore the role of AI in space, it is helpful to first look more closely at what artificial intelligence actually is. AI is a field of computer science focused on developing machines and software capable of performing tasks that normally require human intelligence, such as complex problem-solving, decision-making, and processing natural language. In recent years, the application of AI in space exploration has grown increasingly common. NASA and other space agencies have been actively integrating artificial intelligence into many different facets of their work, including mission planning, the operation of spacecraft, and the analysis of scientific data. One of the most powerful advantages of using AI in space is its capacity to automate tasks that would otherwise demand human intervention. As an example, planetary rovers have been engineered to operate with a high degree of autonomy. This allows them to continue making discoveries and conducting experiments, even when direct communication with Earth is lost. AI-powered rovers can skillfully navigate difficult terrain and carry out scientific procedures without needing direct human commands, which enables scientists to collect more information and make more discoveries. Furthermore, artificial intelligence can process enormous quantities of data far more quickly than a human can. This capability is especially valuable in space exploration, where information from countless sensors and instruments has to be analyzed in near real time to inform critical decisions. AI can also identify subtle patterns within data that a human observer might miss, yielding precious insights into the fundamental workings of the universe. The use of AI in this capacity has already contributed to a number of remarkable discoveries on Mars, including finding evidence of past liquid water and identifying organic molecules, which are the essential building blocks of life. Without the assistance of artificial intelligence, it is likely that scientists would have required much more time to process the immense volumes of information sent back by the Mars rovers to reach their current discoveries. AI can be applied to analyze the vast datasets collected by these robotic explorers and other spacecraft, helping to identify regions that warrant further study. This allows scientific teams to concentrate their efforts on the most promising locations and make the most of their finite resources. However, when it comes to tasks that depend on a high level of creativity or human intuition, AI may not be the ideal choice. For example, the process of designing an entirely new spacecraft or making critical choices in a quickly changing scenario often necessitates human expertise and judgment. The advance of AI has understandably caused concern for some individuals. The technology has progressed at a remarkable pace in recent years, and as it continues to evolve, questions arise about how it will shape our lives. Within the domain of space exploration, as artificial intelligence grows more sophisticated, it holds the potential to take over certain responsibilities currently handled by people. A persistent fear is that AI could one day supplant humans across many sectors, which could lead to job losses and economic disruption. Furthermore, some are apprehensive that AI lacks the capacity for empathy and the creative problem-solving abilities that are so distinctly human. Here, a disclosure is made. The narrator is not Alex McCone, but rather an AI that was programmed to compose this very script about its own effect on space exploration. Yet, had this information not been shared, would it have been possible to discern that the author was not human? This query opens up fascinating philosophical discussions regarding the essence of creativity and the inherent limits of artificial intelligence. It leads us to ask what roles can be fulfilled by AI and just how far its capabilities can extend. Are there certain jobs that will forever demand a human touch? By appreciating the respective strengths and weaknesses of both humans and AI, we can move toward a future where each complements the other, working in concert to achieve even greater accomplishments. To elaborate on this concept further, one of the primary benefits of AI is its capacity to analyze enormous quantities of data with speed and precision. For instance, AI is transforming how spacecraft are conceived and constructed through a method known as generative design. This is a process where an AI system produces numerous potential designs for an object, all based on a specific set of constraints and requirements. The system then employs machine learning to continuously refine and optimize these concepts, considering factors like weight, structural integrity, and material efficiency. This approach can yield highly innovative designs that might not have been conceived through conventional human methods. AI is exceptionally well suited for this kind of work because it can process huge amounts of data and execute complex calculations rapidly. It is also able to learn from previous designs and analyze information to find patterns and ideal solutions. Moreover, an AI can generate a far greater number of design possibilities than a person could in the same time frame, which increases the probability of discovering the best possible outcome. Ultimately, using AI in generative design for spaceship components has the potential to yield stronger, lighter, and more efficient parts, thereby improving the overall performance and safety of space missions. While AI excels at performing repetitive and data-intensive tasks, there are still areas where human intelligence remains indispensable. Creativity and critical thinking are crucial for addressing problems that fall outside the boundaries of routine procedures or pre-programmed algorithms. In situations involving an equipment or spacecraft malfunction, for instance, these human skills are needed to devise inventive solutions that might not have been previously considered. Such abilities are not yet something AI can replicate. Although AI can generate novel ideas by analyzing data for patterns, it still does not possess the human capacity for true imagination and originality. AI algorithms are built to optimize performance and reach predefined goals, whereas human creativity often emerges from the exploration of the unknown without a clear set of objectives. Through its own research, the AI acknowledges the tremendous advantages it can bring to space exploration, from operating autonomous rovers and designing spacecraft components to analyzing vast datasets and searching for intelligent life elsewhere. As an AI, however, it is also aware of the constraints of its own programming. It may be capable of analyzing data and offering insights, but it cannot feel the sense of wonder and awe that a person feels when looking up at the stars. It cannot experience the surge of excitement that accompanies a new and unexpected discovery. These are uniquely human experiences that an AI can only observe and attempt to comprehend. The concern that AI could eventually replace people in many fields, causing job loss and economic turmoil, is a significant one. It is important, though, to remember that AI has its limitations. Certain tasks will always call for human intuition, creativity, and emotional intelligence. Instead of aiming to replace humans, AI ought to be regarded as a tool to augment and enhance human abilities. By collaborating, humans and AI can accomplish remarkable things and confront some of the world's most urgent challenges. After the AI's portion concluded, the human creator offered a personal note, asking his audience for their impressions of the video. He expressed his hope that they found the experiment enjoyable and was curious if they thought the AI had written a good script for his channel. He also wondered if its non-human origin was apparent before the reveal. He invited viewers to share their thoughts in the description below. For his part, he admitted that at moments he was surprised by its voice, which was strikingly human in its cadence. However, he also revealed that creating the script required extensive prompting before the AI produced the final version. He then posed the question of whether he might one day be replaced by an AI, concluding that while it is a possibility, the technology currently lacks a true creative spark. Without human input and direction, its output was flat and uninspired. He also noted that the process took much longer than writing a typical script, as coaxing the desired quality and accuracy from the AI proved to be disproportionately tedious. He therefore assured his audience that this was a one-off event, and that his next video would be produced by a human hand once more, or so he claimed, adding that this is precisely what an AI would say. When you look into the sky on a clear night, you will see thousands of stars stretching across the view. These stars are a beautiful reminder of the cosmos in which we live. It is a curious observation that when we examine the many images released by space agencies, the backdrop of space often appears strangely empty. A question naturally arises from this. Why is the star field missing? It would seem that without an atmosphere to obstruct the view, the countless stars in any given direction should be brilliantly visible. In fact, this very phenomenon was noted by the Apollo astronauts, who reported seeing no stars from the surface of the moon, where there is no atmosphere at all. The explanation for this lies in the fundamental way that both our eyes and cameras function. When we view something very bright, the iris in our eye constricts, reducing the amount of light that enters. This is precisely what the Apollo astronauts experienced. Although no atmosphere was present above them, the intense sunlight reflecting off the lunar surface caused their eyes to adjust as if it were a bright day on Earth. One astronaut recounted that he could only make out a few of the most brilliant stars when he stood within the shadow of the lunar module, looked straight up, and lifted his protective visor. One can only imagine the breathtaking panorama of our galaxy that astronauts might witness if they were to land on the night side of the moon, allowing their eyes to fully adapt to the near-perfect darkness. A similar principle applies to the cameras aboard spacecraft. When a probe is imaging a planet, its shutter speed, the duration the shutter remains open to let in light, is calibrated for what are essentially daytime conditions, because the target is usually the sunlit side of a world. This exposure time is far too brief to capture the faint light of distant background stars. On occasion, however, a mission's objective is to photograph the night side of an object. To do this, the exposure time must be significantly increased to gather more light. When this adjustment is made, the background suddenly fills with a multitude of stars. A time-lapse sequence of raw images from the Cassini spacecraft illustrates this perfectly. We can see that Cassini captured a wide variety of pictures using different exposures. In some, no background stars are apparent, while in others, the star field is dense. This brings us to another important detail about the images that space agencies share with the public. You have likely seen some of the magnificent portraits of Saturn, but what may not be obvious is that such a view is not a single photograph. Instead, it is a composite, a mosaic carefully assembled from many individual images. In these mosaics, background stars are almost never seen because the dark, empty sections of space surrounding the main subject are typically not incorporated into the final stitched-together image. Many spacecraft employ this technique. The primary reasons are that it can vastly improve the final resolution of the picture and also minimize the amount of data that needs to be sent back to Earth. Bandwidth is an extremely precious resource in deep space, where data transmission speeds can drop to as low as 2 kilobytes per second at the greatest distances. So, this clarifies why stars are generally absent from the background of images taken in space. It is now beyond the orbit of Neptune, so far away that no telescope can ever study it again. Its true nature and origins are a mystery that continues to fuel passionate discussion within the academic community. Was it a piece of a shattered planet sent hurtling toward us from a faraway star? Or could it have been a piece of alien technology dispatched into our solar system, either by accident or with intent by some enigmatic intelligence? It may be surprising, but there are still academics who propose both of these theories as plausible explanations. The anomalous behavior of Oumuamua makes it challenging to classify it definitively as a comet, an asteroid, or something artificial. Yet, reaching such a classification could be crucial, as 6 new objects have since been found in our solar system that exhibit Oumuamua's most perplexing characteristic, an ability to accelerate without any obvious source for that acceleration. I am Alex McCulgan, and you're watching Astram. Today, we will delve into the mystery of Oumuamua and these 6 new objects, aptly named dark comets, and we will explore the theories that have emerged in recent years as scientists try to account for something that has so far resisted a clear explanation. To briefly recap, Oumuamua is the first interstellar object ever recognized to have entered our solar system. Its arrival was noted on the 19th of October 2017 by observers at the Haleakala Observatory in Hawaii. Scientists very quickly realized there was something unusual about this visitor. It was small, estimated to be between 100 and 1,000 meters in length, and was thought to possess a highly unconventional shape, possibly like a cigar or a flat disc. Its trajectory and velocity made it evident that it would eventually depart our solar system, leading scientists to conclude that it must have originated elsewhere. The object was consequently given the Hawaiian name Oumuamua, which translates to scout or first distant messenger, acknowledging its status as the first of its kind known to us. While it is almost certainly not the first interstellar object to have ever passed through our solar system, as there are trillions of potential candidates that have likely done so, scientists were eager to study Oumuamua to see what traits it might have that would make it similar to, or different from, the objects native to our own cosmic neighborhood. As their observations continued, they started to identify certain anomalies. Although Oumuamua was at first classified as a comet, it soon became clear that it lacked a coma or a cometary tail, which made it appear more like an asteroid. This absence of a coma, however, became a significant puzzle when Oumuamua was observed accelerating away from the Sun as it began its slow journey out of our solar system. The acceleration itself was slight, only about 17 meters per second when it was closest to the Sun, yet this was enough to create a stir in the scientific community. Oumuamua was not behaving as the laws of physics predicted it should. Over the next few months of observation, it was confirmed that Oumuamua was deviating from its path. In physics, an object can only accelerate if a force is acting upon it, so scientists began searching for what could be pushing Oumuamua. A couple of initial hypotheses were quickly dismissed. It did not appear to be a simple nudge from solar winds. While the tiny particles streaming from the Sun are known to exert a small pressure on objects in space, this force was not nearly strong enough to explain Oumuamua's acceleration, assuming it was an ordinary asteroid. It is important to note that this is an assumption, as even our best images of Oumuamua showed it only as a minuscule point of light, making it impossible to know its appearance for certain. Most theories about its shape are derived from variations in its light curve, as its brightness rose and fell in a uniform pattern during its travels. This would not occur with a spherical object, but is consistent with an irregularly shaped object, like a disk or a cigar, tumbling through space. This led scientists to consider another category of accelerating objects found in our solar system: comets. When a comet ventures near the Sun, its internal ices warm and undergo sublimation, transforming directly into gas that jets away from the main body. This release of gas and dust not only creates the comet's distinctive tail, but also imparts a subtle push. This force acts like a small thruster on the sun-facing side, causing the comet to accelerate away from the immense heat source. The central puzzle with Oumuamua, however, was that scientists could not find any evidence of this gas and dust. Despite careful observation, the expected cloud simply wasn't there. This conspicuous absence opened the door to more unconventional ideas, sparking a notable debate between two theorists. The first and more widely publicized theory came from Harvard professor Avi Loeb, who suggested in several papers that Oumuamua could be a product of alien technology. He contended in 2018 that the pressure from solar radiation could explain the object's acceleration, but only under the condition that Oumuamua was far thinner than initially thought, somewhere between 0.3 and 0.9 millimeters thick. Loeb argued that a natural object measuring 1,000 meters in length but less than a millimeter in thickness was extremely unlikely, leading him to conclude it must have been artificial. He proposed it was a light sail, engineered to capture solar winds for propulsion on a journey from one star system to another. This hypothesis was met with significant resistance from others in the academic world. Darryl Seligman, then a postdoctoral researcher at Cornell University, offered a counterargument in a 2020 paper he co-authored. He theorized that the reason no outgassing was seen from Oumuamua was because it was emitting an invisible substance, such as pure hydrogen gas. Such a gas would have been undetectable by the telescopes that were observing the object. Seligman's initial proposal was that Oumuamua was composed mostly, or entirely, of solid hydrogen, a kind of hydrogen iceberg that was sublimating in the sun's warmth. It was this sublimation, he argued, that provided the gentle push. Loeb disagreed with this premise. A few months later, he co-authored a paper questioning where such a hydrogen iceberg could have possibly originated. Through mathematical modeling, he demonstrated that the faint starlight in the interstellar medium would be warm enough to vaporize any hydrogen iceberg formed in even the closest, densest molecular clouds long before it reached our solar system. Loeb remained firm in his belief that an extraterrestrial explanation was the most plausible one. The strength of his critique effectively sent Seligman back to reconsider his hypothesis, leading him to abandon the hydrogen iceberg model. Nevertheless, Seligman remained captivated by the underlying idea that escaping hydrogen gas was the driving force behind Oumuamua's motion. For a time, he lacked a clear mechanism for how this could happen, until a pivotal meeting in 2023 with Jennifer Bergner, an assistant professor at the University of California. Bergner drew his attention to laboratory experiments where water ice, when irradiated in extremely cold environments, could trap pockets of hydrogen. This trapped gas would then be released later as the ice warmed and its internal structure rearranged. This insight was particularly compelling because both water ice and cosmic radiation are common in space, suggesting that the necessary pre-baking could occur naturally. Working together, Seligman and Bergner authored a paper that argued Oumuamua represented a new class of object altogether. It was neither a conventional comet nor an asteroid, but rather a dark comet, one possessing a coma that was present but invisible. Their explanation accounted for Oumuamua's acceleration and also for the missing dust, as a dark comet would not need to shed dust. Instead, it would release its trapped, invisible gases as its structure reconfigured, a process far gentler than the volcanic-like eruptions from a typical comet's surface. This revised theory still failed to convince Loeb, who in the following month co-authored 2 more papers that criticized Seligman's mathematics and continued to advocate for his alien spacecraft model. By then, Seligman was already exploring the next logical extension of his work. He began to wonder if Oumuamua was a dark comet. Could there be others like it closer to home? He, Bergner, and other colleagues began to sift through existing data on objects within our own solar system. While these objects wouldn't be interstellar, their search was for anything that was accelerating when it shouldn't be. Their investigation soon paid off, revealing 6 candidates that met their criteria. These were 6 objects that exhibited non-gravitational acceleration not caused by solar wind, a motion that could not be explained by any known mechanism. The objects themselves were small, some as tiny as 3 meters across, and appeared to be unremarkable asteroids with no notable features. They were all near-Earth objects, orbiting in a way that made them highly accessible for future missions, and every one of them showed signs of this faint, unexplained acceleration. It is important to clarify that this acceleration is incredibly minor, so small that it had been previously overlooked. These objects are not zipping around the solar system like spacecraft. They are not interstellar visitors, but just like Oumuamua, their motion is currently a scientific mystery, especially given their lack of any visible outgassing. Intriguingly, one of these objects is already slated for a visit by 2031. The object, 1998 KY26, is a planned target for the Japanese Hayabusa 2 probe. This probe is part of an asteroid sample return mission launched in 2014, which, after completing its primary objective 6 years later, received a mission extension to visit other asteroids in the near-Earth Apollo group. 1998 KY26 is a rapid rotator, spinning once every 10 minutes, and Hayabusa 2 will perform a flyby to gather more data on this small, water-rich body, which could benefit future human missions to Mars. Once the probe arrives, it might provide clarity on the source of 1998 KY26's strange acceleration. With Oumuamua itself now far beyond our reach, it is not clear which of the scientific theories is correct. We may never know for certain, but the discovery of more objects with similar anomalous acceleration is undeniably fascinating and will very likely provide deeper insight into Oumuamua's possible nature and origin. If these local objects are found to be propelled by the invisible outgassing of hydrogen, Seligman's theory will be strongly supported. If, however, a small hatch were to open and a tiny alien were to wave before speeding out of the solar system, then we might regret not having paid closer attention to Loeb. The former outcome seems more probable than the latter, as we have excellent images of 1998 KY26, and it is clearly not a light sail. Either way, it will be a fascinating object to study. Of course, in the final analysis, it may turn out that neither theory is correct. This is the wonder of science. The more we explore the universe, the more we encounter phenomena that are strange and unexpected. The more we learn about cosmic visitors, the more refined our theories become, and perhaps future encounters with interstellar objects akin to Oumuamua will lend decisive weight to one explanation over others. The search for unseen objects, guided only by the invisible forces they exert, has always stirred within me a profound sense of wonder. When the year 2031 arrives, it's possible this quest for understanding will find some resolution, or maybe we will simply discover an even deeper well of questions. In the end, only the passage of time will reveal the answer. For nearly the entirety of human existence, the night sky has been our map, a celestial guide that led us across vast continents and lit our way into the future. The stars are woven into the fabric of our civilization just as deeply as the land and the oceans. Yet, that timeless sky is now undergoing a transformation. While the stars, nebulae, and supernova remnants burn as brilliantly as they ever have, very few of us will have the opportunity to see them as our ancestors did, even though restoring that view would require little more than the flip of a switch. This exploration will show how the heavens have altered within our own lifetimes, uncovering the significant consequences that artificial light, both seen and unseen, has had on us, on delicate ecosystems, and on vital scientific endeavors. We will examine how a green revolution, despite its good intentions, actually exacerbated the problem. We will see how we have launched our own artificial constellations into orbit, and even how the natural constellations are themselves slowly changing. Indeed, we will look forward to see how our sky will appear in 1,000, 1,000,000, and even billions of years from now. As with any slow, incremental change, we seldom notice it as it occurs. But on rare occasions, that gradual process can be starkly revealed in a single moment, as it was during the 1994 earthquake in Los Angeles. In the pre-dawn hours of January 17th, a significant portion of the city's power grid failed, instantly stripping away the veil of decades of accumulated light pollution. Residents evacuating their homes were so taken aback by the spectacle above that some simply stood in awe of what had always been there, hidden just beyond the city's glow. One person was so bewildered that they called the local observatory to inquire about the enormous, silvery cloud stretching across the sky. The unfortunate truth is that the sky you remember from your childhood stargazing is not the sky that exists today. Between the years 2011 and 2022, light pollution increased at an average rate of 10% per year, which means its intensity more than doubled in that short span. So let us imagine a journey to a true dark sky location on a clear night, far from the luminous haze of towns and cities, to appreciate what has been lost before we explore how we might reclaim it. There is a practical tool for rating the visual quality of the night sky known as the Bortle scale, which runs from a rating of 1 to 9. In the heart of a city, beneath the most illuminated skies, you might be able to count just 100 stars, a classic Bortle scale 9. As you travel away from the lights, however, the sky begins to unveil more of its secrets until it becomes almost unrecognizable. Driving out into the surrounding urban areas, the sky darkens to a Bortle 7. Here, on a transparent night, you might just discern a hint of the Orion Nebula, appearing as little more than a fuzzy-looking star, while any clouds overhead would be brightly illuminated. Once you have passed the city limits and entered the rural countryside, you find yourself under Bortle 3 skies, where much more of the cosmos comes into view. The star clusters designated as Messier objects 15, 4, 5, and 22 are now visible to the unaided eye. The Andromeda Galaxy is clearly present, and with a careful look, you can spot the Triangulum Galaxy, at distances of 2.5 to 2. 7 million light-years, these two galaxies represent the most remote objects we can perceive without optical aid. And that giant, silvery cloud seen over Los Angeles, that is our own Milky Way, a diffuse band of light arcing overhead, composed of more than 100 billion stars. Finally, after several hours of travel, you arrive under Bortle 1 skies, a truly pristine dark sky site. Where we began in the city with only 100 visible stars, here you can see thousands. It might even take a few moments to recognize the constellations you thought you knew, as they become lost within the breathtaking detail of this profoundly dark canvas. If you are fortunate enough to be in the southern hemisphere, your gaze will be directed toward the galactic center, and you might even notice it is bright enough to cast faint shadows on the ground. For those of us in the northern hemisphere, there is no need for envy. Our view will be reversed as our solar system orbits to the opposite side of the galaxy in a mere 120 million years. Portions of the magnificent Orion complex, a star-forming region spanning 1,200 light-years that includes the Horsehead, Flame, and Orion nebulae, are visible from both hemispheres. Though binoculars are highly recommended, the nearest object that is fully revealed in such profound darkness produces no light of its own. This is interplanetary dust, which is gently illuminated by the sun to form a faint band known as the zodiacal light. This band stretches from one horizon to the other and features a brighter patch called the Gegenschein, which appears in the sky directly opposite the sun's position over the constellation Virgo. Regrettably, those of us who reside in cities are effectively trapped in a perpetual, artificial twilight, never experiencing a genuine night sky. This condition has unforeseen consequences for us as well as for the heavens. So how can a few streetlights manage to obscure an entire galaxy? The answer, in a single term, is sky glow. Any light that escapes upward into the atmosphere is subject to being scattered in all directions by air molecules and aerosols. The portion of this light that is reflected back toward the ground, entering our eyes or our telescopes, is what we perceive as sky glow. Its effect is to dramatically lower the signal-to-noise ratio of faint light arriving from space, which impairs our ability to see and to study celestial objects. You may have had a similar experience while driving on a dark, foggy night. In an effort to see the road more clearly, you might have switched on your high beams. The slight upward angle of these powerful lights illuminates the fog directly in front of you, which scatters the light and produces the opposite of the intended effect, bleaching out your field of view and making the road ahead even more obscure. To compound the problem, it is not just that the sky has become brighter. The tragic outcome is that our eyes themselves have become less capable of seeing in the dark when we step outside. Human eyes possess an incredible natural capacity to detect brightness across 9 full orders of magnitude. This is possible because we have 2 distinct types of vision. The first, which you are using at this moment, is called photopic vision. It is our daytime, color-sensing sight, handled by the cone cells in our eyes. The second is scotopic vision, an extraordinarily sensitive monochrome night vision that is recorded by our eyes' rod cells. It is this scotopic vision that enables us to perceive the most delicate details of the night sky. Contemporary lighting is diminishing our capacity for scotopic vision, a consequence of the fact that not all light is perceived equally by the human eye. The last decade to 15 years has seen a widespread shift toward energy-saving LED lights, which has altered the spectrum of light pollution itself. We've moved away from the familiar orange tones of sodium lamps and into the blue-green frequencies characteristic of LEDs, a part of the spectrum to which our eyes are acutely sensitive. These specific blue-green wavelengths have the effect of slowing our dark adaptation, or in a more severe scenario, can undo it entirely in just a few minutes. This is the underlying reason why astronomers and pilots operating at night are often seen using red-hued lights or goggles, a simple measure to preserve their scotopic vision. To achieve our full night vision potential, we need a near-total absence of short-frequency light for a minimum of 30 minutes, and this adaptation can continue to develop for as long as 2 hours. A natural question then arises: if our eyes are so responsive to the blue frequencies in typical LED lights, why not simply use less of that light to curb overall light pollution? The logic is sound, and in theory, we could do just that. The reality, however, is quite different. The remarkable efficiency of LEDs, when compared to older sodium and filament bulbs, means we conserve both energy and money, even when the lights are operated at a much higher brightness. Consequently, this is often exactly what happens. We make them brighter, partly because of a collective feeling of safety in well-illuminated spaces, even though statistics do not show a corresponding decrease in our likelihood of being a victim of crime. Our eyes also possess retinal cells that play no role in sight, but are instead integral to regulating our internal body clock. It turns out these cells are also especially sensitive to shorter wavelengths of light. This means that artificial illumination, and LEDs in particular, do more than just obscure our view of the night sky. Their effects on us are more profound and potentially severe. The interruption of our circadian rhythms by artificial light disrupts the body's production of several vital hormones, most notably melatonin. What's incredible is how this can set off a dramatic cascade of effects throughout the body, potentially leading to metabolic issues, mood disorders, and in the most serious cases, cancer. While for humans, there is at least some perceived benefit to artificially extending the day, for the rest of the natural world, the consequences are almost universally negative. Artificial lights interfere with the circadian rhythms of wildlife as well, disrupting critical patterns of sleep, migration, reproduction, hunting, and even evolution. Nearly every species that has been studied to date shows negative impacts from lighting, affecting both individual animals and their entire populations. Scientists have observed these effects in a vast range of life, including fishes, birds, amphibians, insects, and other invertebrates, as well as in ecosystems hundreds of meters below the ocean's surface, and even in trees. For instance, deciduous trees, which naturally shed and regrow their leaves annually, can be tricked by constant light into keeping their foliage year-round, a state that induces stress and can ultimately prove fatal to the tree. There are straightforward measures we can take that offer the rare combination of saving money while also improving our well-being. The most effective action, of course, is to switch off lights that are not needed, especially outdoor lighting and any fixtures that shine upward. When installing or replacing lights, it's wise to choose low-power LEDs with a low color temperature, such as 3000 Kelvin instead of 5000 Kelvin. Furthermore, well-designed lighting incorporates shielding to direct the light precisely where it is required, which minimizes the excess glow that escapes into the atmosphere. But beyond the challenge of ground-based artificial lights, we are now contending with a significant new source of light pollution originating from space itself. On October 4th, 1957, the Soviet Union launched Sputnik 1, which became the first satellite to orbit the Earth. In the decades that followed, the number of active satellites grew at a steady pace, increasing by an average of about 30 per year in the 60 years leading up to 2017. Starting in 2018, however, Elon Musk's SpaceX began an operation of unprecedented scale. Since 2018, SpaceX has launched nearly 7,000 satellites into space, along with a single Tesla Roadster. As things stand today, SpaceX has twice as many active satellites in low Earth orbit as all other companies and countries on the planet combined. While many have seen graphs with steep upward curves, this particular one is truly stratospheric. The overwhelming majority of these new satellites have been placed in low Earth orbit at an altitude of just 550 kilometers. The United Nations Office for Outer Space Affairs has projected that an additional 100,000 satellites could be launched within the next decade. Currently, there are no regulations that cap the number of satellites that can be deployed, and many of the existing agreements and understandings about mitigating light pollution are informal. These satellites in low Earth orbit are especially problematic for light pollution, as they contribute to overall sky glow and create bright trails in both amateur and professional research images, sometimes rendering them completely unusable. Astrophotography often demands long exposures that can last for several minutes, making it highly probable that the trails of passing satellites will be captured during that time. An image of the Horsehead Nebula clearly shows 3 such trails, and this is a phenomenon I have even witnessed in my own photographs of the Orion Nebula. The impact of satellites on visual astronomy is easy to see. We can even watch them streak across the night sky in real time. But these man-made constellations, which provide us with GPS, mobile communications, and satellite internet, also operate within the radio spectrum. Their signals span megahertz and gigahertz frequencies, which can create potential interference for scientific observations. Radio signals are uniquely able to pass through galaxies, solar systems, interstellar gas clouds, and Earth's atmosphere, unveiling secrets of our universe that would otherwise remain concealed. This makes it all the more remarkable that the radio signals from a household Wi-Fi router struggle to penetrate a few simple walls. Radio astronomy was instrumental in determining the shape and rotation of the Milky Way, discovering quasars and pulsars, and detecting organic molecular species such as cyanide, ammonia, water, and even amino acids within interstellar molecular gas clouds. It was a radio telescope in Ohio that, in 1977, received the renowned WOW signal. The signal was detected at 1,420 megahertz, a frequency theorized to be a logical choice for an alien civilization attempting to communicate, and it is now protected from commercial use to keep it clear for listening. It is, however, still a matter of debate whether the WOW signal was a result of terrestrial interference or a genuine extraterrestrial event. But while we consider how our communications can interfere with astronomy, it's interesting to note that astronomy can also interfere with communications. In 1978, Arno Penzias and Robert Wilson received the Nobel Prize in Physics for their discovery that the persistent interference in their antenna was not, in fact, caused by pigeons. What they had found was the cosmic microwave background. This was the cooled remnant of the universe's very first light, and the detection of this faint, low-level hum in their Bell Labs antenna and the understanding of its origin served as powerful confirmation of the Big Bang hypothesis. In a remarkable instance of serendipity, the radio emissions from the black hole at our galaxy's center, Sagittarius A star, were first identified because they were interfering with transoceanic telephone calls. Stories like this are compelling because they seem to capture the essence of human ingenuity and our innate curiosity. The simple act of pausing amidst the forward rush of technological development to observe an anomaly led to two profound discoveries. A great deal has been revealed within the radio wave spectrum, but even deeper mysteries remain to be explored. For this reason, the Square Kilometre Array Observatory is now being constructed in designated radio quiet zones. It is, without exaggeration, the most ambitious radio observatory project ever undertaken. Its declared objectives include probing the cosmic dawn to witness the emergence of the first stars and galaxies, and to challenge Einstein's general theory through the indirect observation of gravitational waves. The project also aims to investigate the origins of life, search for extraterrestrial intelligence, and deepen our understanding of how pressures like entropy, gravity, and dark energy are shaping our galaxy and the universe. But how does this constant change manifest from our vantage point on Earth? When we gaze at the stars through a light-polluted sky, space can seem stagnant and unchanging. It can be easier to imagine we are on an elaborate film set, with fixed lights for stars, than on a planet moving through the cosmos. Under a truly dark sky, however, nothing feels still. We gain a palpable sense of our journey through space and time. Our planet is orbiting the black hole at the galactic center at a speed of 828,000 kilometers per hour. We are simultaneously moving away from the galactic plane while also hurtling toward the core. Our perspective, along with every object we can observe, is in constant motion. A visualization from ESA, using data captured by the Gaia telescope, reveals how our night sky is genuinely transforming. In 1,000 years, only the most dedicated astronomers would be able to discern a difference in the constellations we see today, although we might be fortunate enough to witness Betelgeuse becoming a supernova. Looking forward about 10,000 years, we will have a new North Star. Polaris will have drifted away from the celestial pole, its position taken by the brighter star Vega. If we examine the constellation of Orion and its neighboring stars more closely, we see they will alter dramatically over the next 450,000 years. The familiar shape of Orion's sword will shatter and his bow will disintegrate. Expanding our view to the entire night sky, we can watch our galaxy evolve over a span of 4.5 million years, with Orion visible in the bottom right. What this data cannot predict, however, is how many more stars will go supernova or how many new ones will be born. For that, we can only wait and observe. Over the next few billion years, the sky will start to appear so different that one might think we had traveled to another galaxy entirely, and in a sense, we will have. The Andromeda galaxy currently occupies about 3 degrees of our sky, which is equivalent to the width of 6 full moons. It is accelerating in our direction and is projected to arrive in roughly 5 billion years, at which point it will dominate our view. Because galaxies are so diffuse, Andromeda and the Milky Way are expected to pass through one another with relatively few direct impacts. But it is the unseen force of gravity all around us that will ultimately determine our fate. Over the subsequent 5 to 10 billion years, our two galaxies will engage in a gravitational dance, gradually distorting one another. The mixing of their vast gas clouds will trigger a tremendous burst of star formation, transforming two distinct spiral galaxies into a single, enormous elliptical blob. Witnessing this cosmic event from Earth, however, would likely be impossible. as the sky would be saturated with the intense light of our own sun, which by then will have expanded into a red giant. In 1 trillion years, the very last star will form. From that point on, only decay awaits the universe. The galaxies we can currently see beyond our local group will grow faint and dim, eventually receding beyond the edge of our observable universe. In 120 trillion years, all stars will have finally been extinguished, and the night sky will fade into complete blackness. As is often true in our complex world, our actions can lead to unforeseen consequences. Our night sky is changing in multiple ways, and while it has been obscured, it is not yet lost. Around the world, towns, cities, and governments are starting to recognize the importance of this issue. They are beginning to make changes in local ordinances and laws to protect our view of the cosmos and the nocturnal wildlife below. If this journey through time has inspired you to seek out a dark sky or to help reduce your own impact, you can learn more at darksky.org and explore light pollution in your area at lightmap.info.